All right, AP Calc, let's move on into the second half of section 9.3. And in this section, we're again going to be dealing with some differential equations that are too difficult for us to solve outright. So we're going to work on approximating our solutions. And unlike the graphical solutions that we came up with here in the first half of 9.3, which we got by using slope fields, now we're going to move into something called numerical approximations. So we're not going to be able to actually solve the diffie q and know what y is, but we are going to be able to come up with a list of values here, ordered pairs basically, that are going to do a pretty decent job of mimicking the solution curve to that particular diffie q. And with some cool tricks on our calculator, we're going to be able to find that these solution curves are going to be pretty darn accurate here. Not perfect. They are still approximations, but they're going to get us relatively close. So this method here is called Euler's method. Once again, named after that Swiss mathematician Leonhard Euler, who you've come across his name a lot during the course of the year. Now, in an Euler's method problem, three things are going to be given to us, guys. First of all, you're going to be given right here a differential equation. That shouldn't surprise you. In every diffie q problem, which is what we're doing here in chapter 9, they give you a derivative. A second thing they're going to give you right here is an initial condition. X naught, Y naught is what we're going to call that ordered pair. And this is going to be very similar to the initial conditions we were given to solve initial value problems back in section 9.1. And the third thing you're going to get now that's different, we haven't seen this before, is a value of delta x. And of course, if you remember here, guys, with delta x, that just means the change in x. So basically, we're going to be starting from a particular point right over here. And we're going to be finding a delta x and a delta y in order to get to our second point. So take a look at this very sophisticated graph that I have down here on the bottom of the page, guys. This point right over here is going to be considered our starting point. So I'm going to call that point A, and the coordinates of point A are going to be x naught, comma, y naught. That's the ordered pair they're going to give you at the beginning of the problem. And then what we're going to do is we are going to know what delta x is. That'll be given to us, and that delta x will tell us how far to move to the right from point A. We're then going to have to figure out, and that's the whole challenge of what we're doing here, the value of this delta y over here, which will tell us how far up to move from point A. So when we move the delta x to the right and the delta y, which could be either up or down, that's going to get us to our second point right now, which is going to be called point B. But a little bit more specifically, the notation I'm going to use for that is x1, comma, y1. And you'll notice those subscripts follow from the x naught, y naught. So we'll be given delta x. We've got to figure out delta y. Now, how are we going to do that? This is kind of interesting right here, guys. If we were to think about the slope, and I should be specific now, the slope of this diagonal segment right over here, how do we get from point A to B? We rise a certain amount. I went right over my arrow there. And then we run a certain amount right there. And as I think you can tell, that rise is the same as the delta y over here on the right. The run is the same as the delta x down there on the bottom. So this should seem really obvious when I write it down. The slope of this diagonal line segment is change in y, or delta y, over change in x. And of course, that's just the formula for slope, delta y over delta x. So, that seems kind of silly. But now, here's the interesting thing here, guys. In this problem, the hard part is going to be coming up with the value of delta y. We're going to know what delta x is because they'll give it to us, and in a roundabout way, the derivative that they give us right here tells us the slope of the tangent line, so we're going to know what m is, which means we can solve for delta y simply by multiplying both sides here, we'll cram that in there, times delta x. So we end up with this simple but kind of important formula here, guys. You can find delta y by taking your slope and multiplying that by your delta x value. And like I said, that's a really simple formula right there, but it's actually pretty powerful here for helping us figure out what delta y is when that's not going to be given to us. So that's kind of the gist of what's happening right here. And now I'm going to show you guys a really scary graph that kind of illustrates what's happening within this problem right here. So here's what's going on, guys. Let me just keep it right here for now and say, okay, this is pretty good. So here's what's happening. Let's just read this this off the top right here. We can find a series of ordered pairs that will approximate. Now, again, there's that word. We're not finding the exact solution because some of these diffie-q's are too complicated to solve, but we can approximate the solution curve to that diffie-q with this method right here. And guys, this box I have is not really the big takeaway right here. This, I hope, is obvious. X sub n minus 1 is equal to x sub n and then plus delta x. Okay, what are we saying here, guys? For any x value that you were given, you can find the next x value by taking that previous x value and adding what delta x is. So if you take a look at this big scary graph, right here we're starting at an x value of x naught. So if this is point A right here, everybody, yeah, x naught, y naught, just like we labeled it the last time. But what's going to happen here, and the reason I drew all of these red vertical lines on this graph, is that the new x values are incredibly easy to predict. They will tell you what the value of delta x is. And so, everybody, this delta x that I have right here, oh boy, in blue, also applies right here, and right here, and right here. Delta x remains constant, everybody, and that's the big important thing to realize about that. So this is going to be really simple and very easy to predict what your next x value is. So it's not hard at all to come up with the values of x1, x2, x3, x4, and as far as we needed to go with this. Now what is challenging, though, is figuring out the value of the next y in this sequence right here. y1, y2, y3, and all the way down to y4. So the method we're going to use to do that, everybody, builds upon what we wrote down just a second ago right here. That delta y can be found by taking the slope of your tangent line and multiplying that by your delta x value. So if we go to this graph over here, here's essentially what's happening now, guys. At point A, right over here, okay, we know the location of that point because x naught, y naught will be given to us. And we can use the derivative. Now remember, this green curve I have here is meant to approximate the solution, but you won't know that solution at the beginning. But you will know the derivative. So you can use that derivative and that starting point to graph a tangent line to that curve right there. Okay, and what's going on here, guys? We want to know, where is point B located? Point B is located at this x value right here, x1. So even though I didn't draw a terribly straight line, this would be point B located right here, and its coordinates would be x1, comma, y1. Now, how do we figure out what that y value is? We are essentially, let me do some of this again in purple right here, creating this right triangle right here, and we're going to find y1 according to that formula we wrote down just a second ago. y1, the next y value, comes from taking the previous y value, y naught, and then adding to that your delta y. And your delta y was the slope multiplied by that delta x value right there, m times delta x. And that's how we're going to find y sub 1. And I think I'm getting ahead of myself here, guys, because I think I have that written down here on the bottom. It looks like what I did in blue was I tried to write the point slope form equation of that first tangent line right there. So it's not that. So it's y coordinate minus y coordinate is equal to your slope, whatever that is, times second x minus first x. There you go. And then I think from there I said, all right, let's try to solve for what's going on here. So what it looks like I did now is I added y naught on both sides of that equation. So those canceled. And I put that y naught right out in front there. So y naught times m, x1 minus x naught. And then we noticed, oh, wait a minute, this notation right here, x1, this value, minus x naught, this value, that's going to give you your dx value right there. I probably should have said delta x right there, but okay. So this third line that I have, this one right here, looks very, very similar to the one we had right above it, except the slope expression right here has now become, oh, this is a weird notation, guys, our derivative, our differential equation, evaluated at the previous ordered pair. Now, we don't often see two values right here. Very often we just see an x value, but this derivative could be expressed in terms of both x and y. So everything we have in red there that I just underlined takes the place of the m. And then this x1 minus x naught is just going to become delta x. So this is how you get y1 from y naught. But the thought process would be exactly the same, don't change this in your notes, to find y2 from y1. Or, for example, y8 from y7. So we just kind of avoid the tediousness of writing all that just by using n here to represent any integer. So this formula right here, guys, is the big takeaway. And to translate this into words, you can find your next y value by starting with your previous y value and then evaluating your differential equation at the previous ordered pair, and then multiplying the value of that derivative, which is the slope of your tangent, times delta x to get your next y value. Now, if that sounds complicated, it kind of is, all right? But I think once we dive into some examples, you guys are going to see that it's not too terrible, although that kind of depends on the level of complexity of the problem you're dealing with. Okay, guys, so that's a little explanation. This next slide, I think, is the same thing I just had. I don't know why that's there twice. Okay, so we're going to dive in and we're going to do 3 examples here of varying layers or levels of complexity. This first one, of course, isn't going to be all that bad. By the way, if you haven't seen it before, this is a goofy notation that your textbook uses for the derivative of y. It's the y with the dot over it there. So again, you're given a diffie q. So this is dy dx, which is probably the better way to think about that, but okay. And we're given a linear derivative here, 0.5 minus x. You're given an initial condition right over here, 0.1 comma 2, and you were given the value of delta x, dx in this case. Either one's really the same, and we were told that was going to be a constant. So our x values here are always going to increase by 0.2. So what I'd kind of like to do is start writing some things out. The initial ordered pair that we have here was given to us by the initial condition, 0.1 comma 2. So yay, we know where we're starting. Now the next issue here, guys, is going to be to come up with the second ordered pair. And I already can figure out very easily what this x coordinate is going to be. You take your previous x value, which was 0.1, and then this is what that value changes by. So we're going to add 0.2 to the 0.1 and get 0.3. Now the much harder part is going to be figuring out what that next y value is. So I'm going to kind of use that formula that we wrote down just a second ago, guys. This one right here was y naught. We're trying to find y1. So that will equal y naught plus our derivative now, dy dx or y prime or whatever you want to call it, evaluated at the previous ordered pair, x naught comma y naught, but then that gets multiplied now by dx or delta x. You can use those interchangeably here. Okay, so let's keep going with this, guys, then. y1 is equal to our previous y value, which right there was a 2, and we're going to add to that now the derivative, the differential equation right here, which is 0.5 plus, and in the place of that x, we are going to use the previous x value, which is 0.1. Now, you'll notice there's nowhere to put this y naught right here because this derivative is not expressed in terms of in terms of y at all. So this is a derivative that's expressed solely in terms of x. So that is just there kind of hanging out, but it has no bearing at all, and that'll get multiplied now by the dx value, which we know here is 0.2. Now, we're definitely going to be using calculators here, guys, so I suppose at this point, well, I don't know. How bad would it be? Let's take a look. I think I'm going to run out of luck here pretty soon in terms of being able to do this in my head, but let's see. That would be 0.6. 0.6 times 0.2 would be 0.12, and 2 plus that would be, I think, a 2.12. That doesn't sound right to me now that I look at that right there. Let me go ahead and just type that in and make sure I've got that right. So as I said, guys, we're going to be using our calculators, and I'm starting from scratch just like you guys probably are here. Now, I'm going to show you a faster way to do this in a minute, but let's see what we've got. We had our initial y value of 2. We were adding to that the derivative expression, which was, I believe, a 0.5 minus x, and your previous x value was 0.1. I think that might have been the mistake I just made in my head. Yep, I had a plus right there, not a minus. That's why that answer sounded wrong to me. Sorry about that, guys. So that's 0.5 minus 0.1, not plus. Okay, gotcha. And then we'll close off that derivative and multiply it by 0.2, which is our delta x value, and we get 2.08. All right, so I'll put that right here, 2.08. And guys, we just found the value of y sub 1, 2.08. And there you go. We're making some progress right here. Okay, that's how you find y sub 1. Let me space this out just a little bit better. Now, let's see if we can get a little bit more efficient here at finding y sub 2. So that now equals the previous y value, which was 2, because that was in reference to this number right here, but now it's going to be the 2.08 that we just came up with a moment ago. We'll add to that our derivative, which is 0.5 minus the previous x value, which is now 0.3. And again, we multiply that, parentheses would have been prettier there, we multiply that by dx or delta x, which remains 0.2. So let's type that in, everybody. And again, the numbers aren't that bad right now. I could type in 2.08, but if I just hit plus, it does last answer for me. And then in parentheses, we had a 0.5 minus 0.3. That was our previous x value now, multiplied by 0.2. Okay, gotcha. And we'll hit enter there, and now we get 2.12 for that value here. Okay, so we're moving right along here, guys. Let's take a look at where we're at. Our next ordered pair then is going to be 0.5, because again, these x values just increased by 0.2 each time, and we got 2.12 now for y sub 2. And let's take a look at where we were asked to go. I didn't really pay attention to that. We're trying to approximate the value of y of 0.7. So I think I know already that my next ordered pair is going to be 0.7 comma something. So whatever we get right here, guys, should be our final answer to this problem. So let me zoom in a little bit more here, give myself a little bit more room, and here we go. We're now trying to find y sub 3. So we start with our previous y value, which is now 2.12, and we add to that the derivative, 0.5 minus the previous x value, which is now, interesting, 0.5. We multiply that by 0.2. Guys, I don't think I need my calculator for this one. Our derivative at this point is 0, which means we have a horizontal tangent right there, guys. All right, so that 0 times the delta x is still 0, and this one time, we're going to end up with the exact same y value a second time now of 2.12. And that is the answer we were looking for, guys. Let me say it the way they wanted to approximate y of 0.7. So here's my answer. Y of 0.7 is going to equal 2.12. That's the answer that I got from right there. And that, everybody, is our first approximation of a solution curve we came up to using Euler's method. Now, two big things. Number one, how difficult was that? Well, it certainly wasn't easy, but it's a process, and I'm hoping you guys understood it relatively well. So I'm hoping if you see one like this again, you go, oh, okay, I got some sense of how to do it. But the second question, and the one that is much, much, much more important, is what in the world have we actually just accomplished? Well, what we're not going to do, but we could, is draw ourselves a really quick sketch of what this graph looks like. You guys do not need to put this in your notes, but real quickly, we have come up with 1, 2, 3, 4 ordered pairs. And if we were to plot these ordered pairs, boy, we're not going very far with this graph right here, guys. If that was 2, and this was 1, and that's 1, sure, and this is maybe 0.5. If we were to plot these points, we're at 0.1, comma 2. We're right about here to start. And then 0.3, and then 2.08, so it goes up a little bit higher. And then 0.5, we're at 2.12, and then at 0.7, we're at exactly the same value right there. If we were to connect those, we start to get a sense for what the solution curve to this graph actually looks like. Now that isn't much of a graph, guys, because 4 points, I can see that it's a nonlinear function. It looks like it's increasing at a decreasing rate, and then it kind of levels off, but it really doesn't give us that much info. Now, if we wanted, this is a Diffie-Q that's easy enough that we could probably solve this one by hand. Let me, again, this is not something you would need to do at all, guys, but our derivative, dy dx, was 0.5, I'm going to write that as a 1/2 here, minus x. Well, if I brought this dx over here and then antidifferentiated both sides, antiderivative of dy would be y. This antiderivative would be a 1/2 x minus a 1/2 x squared, and then a plus c at the end of all that. Now, what I want you to notice there, without spending too much time on this, what kind of function is this? It's quadratic, and it's a negative quadratic. So this graph, whatever it is and whatever c is a downward opening parabola. So I would ask you guys to look at this little graph we came up with right here and say, does it look like it could be a downward opening parabola? And it kind of does. You could go a little further and say that even though I don't know what the value of c is, the x-coordinate of my vertex is negative b over 2a. Well, negative b would be, no, I'm sorry, b is 1/2, so negative b would be negative 1/2 over 2 times a. 2 times a negative 1/2 would be negative 1, so the x-coordinate of my vertex is 1/2. 1/2, guys, does that look like it could be the axis of symmetry of your downward opening parabola? Not exactly because of this horizontal component right here, but remember, this is just an approximation. It looks like that could be pretty close. So what I want to show you guys right now is a neat way to use the calculator, not only to save yourself a lot of work once you get used to this method right here, but also to make something meaningful out of the solution that we just came up with right here. So what I'm going to have you guys do with me right now, and this is something that's pretty cool about the Inspire CAS, is we're basically going to build a spreadsheet out of this that'll do Euler's method for us moving forward. Let me show you how this works. We're starting on a calculator page, and we're all going to define our derivative here as a function. So I'm going to go to Actions, and I'm going to go to Define, and we almost always, write this as f1 of x. Now, I tell you what, just because we would rather do things once rather than twice, I'm going to make this function right here, f1 of x, comma, and then I'm going to type a y in there. Now, not every differential equation we're going to use here is going to have both an x and a y, but some of them will. So if we do this just one time, we should be okay in all of those cases. And our derivative here was 0.5 minus whatever your x coordinate is. So you'll notice I didn't put a y there at all, and that's perfectly fine. Now we're going to do something we haven't done, I don't think, you guys, since back in Chapter 2 when we were doing limits. We're going to add a page to this document right here, and we're going to go to Lists and Spreadsheets, which I believe is number 4 for you guys, and we get to something that basically looks like Microsoft Excel or Google Sheets. And we're going to start using formulas here to fill in all of these values for us. The first thing I'm going to do, guys, is click on this heading in the A column right there, and I'm going to label that. And I'm simply going to say those are my x values. So I'll type in an x and hit enter. And then I'm going to go to B, and I'm going to say these are my y values. Okay? You'll see why that's important a little bit later. And this really isn't important, but in column C, I'm going to put in, let's see, I got to do it this way. I'm going to put in here we go, dx, and that's what I'm calling column C. Okay, super duper. Now, we're going to move into cell A1, which is this one right here, and we're going to type in our first x value here, which was 0.1, and we will hit enter. And then, right next to that, in cell B1, we're going to put in our first y value, which in this case was 2. Enter. And then in cell C1, we're going to put in the value of dx or delta x in this problem, which was 0.2. So there you go, guys. We typed in all of our conditions at the beginning of this problem. Now, this is when we start to allow the calculator or the computer to start doing work for us. What's going on in cell A2 now is going to be your next x-coordinate. Now, every one of us looked at this problem, and without any great difficulty, we said, oh, obviously, the next x-coordinate is going to be 0.3, and the next one is 0.5, and the next one is 0.7. Could I just type those numbers in manually? Of course I could, but what fun is that? Let's let the calculator do it for us so that on the next problem, we don't have to go back and retype all of those numbers. To put in an equation, to tell your calculator to do math for you, we start with an equals sign. And we want the calculator to take the number that's located in cell A1. So I'm typing in a location, not a number. It's called a reference. And we want it to add to that value the dx value or delta x value that is found in cell C1. So there you go, guys. And when we hit enter, okay, that got us 0.3. Now, I'm going to go a little bit out of order now. I'm going to skip cell B2 for right now because that's the hard part, and I'm going to go to cell C2. Now, what is dx or delta x the second time we do this? Whatever it was the first time, this remains constant. So again, rather than typing in 0.2, I'm going to put in a reference. And I want cell C2 to equal cell C1. Whatever was in C1 that we typed in manually, it's now going to automatically populate into cell C2. And now the fun part, guys. How do we get our next y value? Okay, so we're going to hit enter, and we're basically going to type in that big formula that we wrote down in our notes not that long ago. Okay, so that formula says that you find your next y value by starting with your previous y value, which is located in cell B1. And then we're going to add to that our derivative, evaluated at the previous ordered pair. Now, if you recall, we named our derivative f1, and then we had two input values here, guys, an x value and then a y value. And the x value is the previous x value found in cell A1, comma, and going along with that is the y value that was found with that too in cell B1. So there we go, guys. That f1 evaluated at A1, B1, that's the slope of the tangent. And now that needs to get multiplied by whatever your dx value was found in cell C1. And yes, I definitely could do cell C2 right there since C2 is the same as C1, but I'd rather make every reference here in row 2 relative to the row above it. So when we hit enter, there's the 2.08 that, yep, sure enough, guys, right there was the second y value that we came up with. It's really y sub 1. Now, that took some time, but here's the payoff, everybody. Computers were invented because human beings got tired of doing repetitive tasks over and over and over again. So now that we've done all of that legwork right here, we can now take advantage of copying and pasting. So you guys can just use your keypad right here. You're going to move up to cell A2. And now for you guys, I believe you're going to hit the shift key and then the right arrow a couple of times. And for me, I'm just going to click and drag. And then when we get there, guys, your keyboard shortcuts on your calculator are exactly the same as they are on every computer you've ever used. Copy is Control-C. So when you guys have those 3 cells highlighted, you're going to hit, now wait a minute, one button at a time. You're going to hit, Control, then let it go, then C, then let it go. For me, I just tap on that and hit copy. Then what you guys are going to do is hold down Shift. While you're holding down Shift, hit the down arrow a bunch of times. Now I'm going to kind of just drag all of this down, and I don't really know or care how many times we're going to do this. I'm going pretty far with this. And for you guys now, you're going to hit Control, then let it go, V, as in Victor, for paste. Okay, for me, I just do that. And I think for all of us, it's going to ask, hey, do you want to overwrite what you have there? And we're going to hit yes. And we all should be looking at numbers that look kind of like this. Now that A column is really, really predictable. Your X values are just going up by 0.2 every single time. The C column is even more predictable because your dx value is just 0.2, but it's that B column, your y values, everybody, that are unpredictable right there. So as we look at them, what do we see here, guys? We started with a y value of 2. Then the function goes up, up, levels off, And now look what happens after that. It starts to decrease. And in fact, boy, it looks like it's decreasing at a decreasing rate right here, which if you think about what we thought we knew about our solution curve, which would be a downward opening parabola, I think it kind of makes some sense here, guys, to think that this parabola could be doing something like this and something like this. So the fact that this thing is now decreasing in value and at an increasing rate right there kind of makes some sense to me, I think. Anyway, the point there is that what we were looking for was the value of y of 0.7, and we got that from the table right there, everybody. When x was 0.7, the y value we expected to go along with it was 2.12. Now, the last thing I want to show you here, because I think this is just awesome that this calculator will do this for us, we're going to add one more page here, guys, to this document, and I don't believe this is something we've done together the entire year. We're going to go to number 5, which is data and statistics. Now, I believe your calculator is going to look just like mine. It's going to be this huge pile of just random points, and I literally, guys, have no idea at all what the calculator is doing right now. But if you look down on the bottom of your screen in the center, it says tap to add variable. I think that happens for you guys too. So we're going to tap that, and I want this horizontal axis to be my x values. So you might need to hit your up or down arrow here, but I'm going to click X, woo, and all those dots kind of move. That was kind of neat. But here's the fun part. Now over here on the left, our vertical axis also says tap to add variable. And on that vertical axis, we want this to be our y values. So when I click Y, prepare to be impressed, everybody. There it goes. And what does it look like we have right here, guys? It looks like we have a downward opening parabola. So this series of dots is meant to give you a visual or graphical approximation to the solution curve to this differential equation, just in case the diffie-q was too complicated for us to solve. Although truth be told, this is one we could have solved by hand. We could have used the initial condition to find the value of c, but I don't want to dwell on that too much. All right, guys. Now, the good news for you is all of this work that we did by hand here in the middle, that's the one and only time we're ever going to do that. I'm not going to make you do that on the next 2 examples, and this will be music to your ears. I'm not going to make you show all that work on your Chapter 9 quest that we are going to take in a little while. You're going to be allowed to use the calculator here to get all of this info. So let's see what we can do right here, guys. There's not going to be much to write from here on moving forward. So what's going on in this problem? Now we have a differential equation that is defined solely in terms of y. The previous one was just in terms of x with no y. This is the other one. This is in terms of y with no x. Here's your initial condition. The ordered pair -2, -3.4, and dx, or delta x, it's really the same thing, guys, has been given to you here as 0.3. You know, as I think about it, we almost always say that dx is a delta x, but it's infinitesimal. It's approaching 0. So since this is a finite amount, I really should be calling that delta x, but textbooks will go back and forth on that. Don't worry too much about it. Really the same thing for our purposes here. So what am I going to do? All right, I'm going to write all this down on a slip of paper so I don't have to keep bouncing back and forth then. So y prime here was equal to y minus the cube root of y. All right, guys, calculator time. So let's go back to our main calculator page. So for most of us, that's probably 1.1. And I don't even need to clear out anything that I have. I can just overwrite it. I'm going to go actions and define, and I am going to define f1, and again of x, comma, and then a y. So this will overwrite the definition of f of x that I have in there currently. And this derivative for this problem now is equal to, and what did I just write down? We have a y, gotcha, and then minus the cube root of y. And if you wanted to put in y to the 1/3, that certainly would be fine too. Okay, and there's our derivative. Now, time to go back to the spreadsheet and overwrite certain things, but not everything. So let's hit Control and then Right for you guys to get back over here. And the first thing I need to do is change my initial condition. The 0.1 and the 2, those were the initial condition from the previous problem. But now for example B, that's changed. My initial condition here is -2 for my x value. And then my initial y value here, instead of a 2, is now a negative 3.4. Okay, so there's the start. The other big change, dx, or delta x, is new now too. This is now going to be 0.3, and I'll hit enter. And did you guys notice that? All of these y values automatically updated. That's cool. And all of your x values now should be in the right spot. They're increasing by 0.3 each time. Now, what we should pay attention to, although I'm not sure if we have to make a change here or not, is this formula in cell B2 now correct? So the next y value, B2, comes from the previous y value, which was B1. We add to that F1, which was the differential equation, evaluated at the previous ordered pair, A1, B1, and then we multiply the value of that derivative, the numerical value, times your dx or delta x, which is 0.3. So the beauty of using the calculator to do this, guys, is that this B column should never need to be changed other than the first value that you put up there in cell B1. So I think everything I need here, guys, is in this table, and I don't even remember what the question was here, guys. They were asking us to approximate the value of y1. So y of 1 would be approximately equal to, and let's see if my table went far enough to find that, right here, guys. When x is 1, it looks like y is a negative 24.293. I'd love to see more digits than that, and I think in your calculator, guys, if you just go over that cell, it'll give you more detail right underneath it. For me, I'm going to assume, always a bad idea, that it rounded correctly. Negative 24.2, whoa, what did I just do? Negative 24.293, and guys, that is our answer right there. Okay, so seriously, once you get the hang of this right here, there's really no work at all to show, and as long as you know how to get everything set up right in your calculator, you're going to be fine. I'm not going to make you guys show nickel and dime work and every nut and bolt that you turn in order to get to that answer. You can just give me this. Now, real quickly, have we learned anything here? Let's try this real quick. If I once again hit Control and then the right arrow, and I get to page 3 in my document right here, let's see if I can do this again right here. If I make those my x values and these my y values, I start to get a function that looks like this. That's a little bit interesting right there. Is that what I thought those y's were going to do? At y1, we're at negative 24.93. All right, well, I think the big takeaway from this right here, guys, is that we've got a linear, it's not quite linear. That's a really tough one to be able to look at to determine if that solution curve makes any sense or not. I guess we're just going to have to assume that it does. All right, so the point I hope I made right here, guys, is that the calculator makes this setup really quick and really easy. The most complicated example I was going to do, probably not surprising, is the last one. And what makes this one hard, guys, is that our diffie-q is now defined both in terms of x and in terms of y. But because we were smart and we set up in our calculator f1 as a function that used 2 inputs, x, y, this really should be a piece of cake now, guys. We really shouldn't have to go back and change anything at all. Even though here, we really only needed it to be f1 of, that was weird, f1 of y. And in the first example, we really only needed it to be f1 of x. But by having both variables there, this is going to go much faster and much easier here. All right, guys. So every time we do a new problem, we kind of do it in the same sequence. We go back to page 1. We redefine our original f1 function, our derivative here. So here we go. This is going to be f1 parentheses of x, y, there you go, is equal to, and this derivative, more complicated than the previous ones, 6x, and then a minus 4x to the third power, and then a plus, we have a y divided by 10. Ooh, I never got out of my exponent. I'm glad I caught that. All right, there you go. 4x cubed, gotcha. And now here we go, plus y over 10. That probably would have made a tough problem much, much tougher. Okay, let me just visually verify. Yeah, that looks good. Our initial condition now was the ordered pair. There it is, -2, -4, and our delta x or dx was 0.2. So back to the spreadsheet, guys. Control right, or we can do it this way. All right, and the initial condition, -2, oh, by dumb luck, that's the same x value, but I got to change this starting y value right here to -4. And the dx needs to change from 0.3 to 0.2. Okay, now once again here, guys, the x values have automatically updated. Each time you go down the list, they increase by 0.2. And my y values here, let's take a look here, right there. My next y value is found by taking my previous y value, cell B1, plus the derivative, which is f1, evaluated at a1 comma b1, and multiplied by your dx value from cell C1. So I've got every reason to think here, guys, that these values are all correct. And this problem, I really did this because I wanted you guys to see you can go pretty far, you kind of have to right here, to find the value of y of 2 would have taken a lot of work to do by hand. In this first example we did, we were really only finding, remember, this was your initial condition right here, so we were only finding 1, 2, 3 values. But in this one here, guys, if we're starting at -2 and we're getting eventually to +2, that right there is a big gap of 4. And your step sizes are 0.2, which is 1/5. We'd have to do this problem 20 times, everybody. 4 times 5 right there from the 1/5 in order to get the value of y2 if we were doing this by hand. As it is, I still may need to extend my table a little bit. Yeah, I don't have an x value of 2 here. So I'm going to go back down to this row right here, highlight those 3 cells and copy them, and then we'll just drag this down, another 4 or 5 times should do it. We will paste. Yes, we're okay overwriting. Oh, I overshot it a little bit, but I think we've got our answer here, guys. 1.299. I'm looking at that cell right. No, not you. You. There you go. 1.299 for the approximation here for y of 2. I should not have had an equals right there. Okay, there we go. And 1.299, and that's our answer to that problem. And this is the one I think I was thinking of right here. If we now were to make a graph, a scatter plot of these values right here, let's hit Control right arrow one more time. And again, if I kind of redefine these variables, there's x. Boy, it kind of fits the window automatically to fit as well, and we get a y right here. So what does this one look like to you guys? To me anyway, it looks like a 4th degree function opening downward. So something that would be a negative x to the 4th, and then some other stuff going on in there as well. And if I thought real quick about what this function looked like, right here, I see a negative cubic term. Its antiderivative then would be a negative quartic, 4th degree term right there. So the fact that I've got that shape right there probably tells me I think we're doing this problem right. I think that solution curve seems to work out pretty well. All right, everybody, that is a wrap then on section 9.3. The good news for you guys, and I want to make sure everybody understands this before we move on, one of 2 things is going to happen. If you're ever asked to do a problem like this by hand, which I have seen on the AP-BC test before, if they ask you to do it without a calculator, it'll be relatively small numbers, like in this problem where we only had to do 3 steps. I think the one I saw on an AP test was only 2 steps, so even easier than that. Or if it's one with a lot of steps, like this one we said was 20, you're going to be allowed to use your calculator in order to do that. And the last bit of good news I have for you guys, I am not going to make you clear out your calculator before you take this test for me or for anybody doing practice APs or anything like that. So you'll be able to walk in with this in your calculator. So hopefully when you see how to do it that way, you go, oh, Euler's method isn't all that bad. All right, everybody, let's give that 9.3 homework a shot. Good luck, and let us know when you have some questions.